Hi there, so this video is on section 1.5, infinite limits. So we're first going to consider the function f of x equals to 1 over x squared. And looking at that function's graph on Desmos, that's what it looks like. Let's look at the equation and confirm with the graph what the domain of f of x is. Now, from our algebra and pre-calc knowledge, we know that the denominator cannot be equal to 0, right? This is a rational function. We know the denominator cannot be equal to 0. And the only value that would make the denominator equal to 0 for this particular function would be 0. So we need to exclude 0 from the domain of f of x. And I can write that in interval notation as negative infinity to 0 union 0 to positive infinity. Okay, so we want to know what happens to f of x as x approaches 0 from the left. Uh-oh, this sounds like a limit. Let me pull this graph back up so we can actually think about estimating these limits graphically. So taking the limit as x approaches 0 from the left of f of x, it looks like as x approaches 0 from the left, that the function is increasing without bound, that it's approaching positive infinity. And then what happens to f of x as x approaches 0 from the right? It looks like the same thing happens. So from both sides of 0, the function is approaching positive infinity. So for our two-sided limit in this case, we are able to say that as x approaches 0, the function is approaching positive infinity. Now here's our informal definition of infinite limit. So a limit in which f of x increases or decreases without bound as x approaches c is called an infinite limit. So if as x approaches c from the right, the function is approaching infinity, and as x approaches c from the left, the function's approaching infinity, we can say that the two-sided limit as x approaches c is also equal to infinity. And then the same thing goes for if the function were decreasing without bound, both one-sided limits are approaching negative infinity, then we can say that the two-sided limit would also be approaching negative infinity. The equal sign for these limits does not mean that the limit exists. This is important to recognize. So the equal sign does not mean that the limit exists. It, remember, tells us how the limit doesn't exist, how it fails to exist by denoting that unbounded behavior for the function. Now, if the one-sided limits were both approaching different infinities, so if as x approaches c from the right, the function is, say, increasing without bound, so approaching positive infinity, and then as x is approaching c from the left, the function is decreasing without bound, so approaching negative infinity, all we would be able to say about the two-sided limit is that it's dne. And then same thing if from the right, the function was approaching negative infinity, but from the left was approaching positive infinity. If those one-sided limits don't match, all we can say about the two-sided limit is dne. So I have a little exploration on this page that if you would like to try this on your own, answer these questions and reference this graph, you can pause the video and try answering these questions. And I'm going to talk us through it. So we have this function h of x that is x squared plus 1 over x squared minus 1. And I've given you a picture of the graph. And it looks like there's a vertical asymptote at -1 as well as +1. So let's answer these next few questions. So the limit as x approaches 1 from the left of h of x. Well, we have the equation for h of x, and notice that if we tried direct substitution, we would end up with 2 over 0. And we've talked about this, that this indicates that whenever we try direct substitution and we get a number over a non-zero constant over 0, that indicates that there's a vertical asymptote. Now, since this is a one-sided limit, we want to know whether, we know there's a vertical asymptote, but we want to know whether the function is either increasing without bound or decreasing without bound. Reading this graph, it looks like that as x approaches 1 from the left, the function is actually decreasing without bound. We could confirm this by thinking about substituting a value directly to the left of 1 in for x. So doing like a test value, where if we get a positive value from that test value, it would mean that the graph is approaching positive infinity, whereas if we get a negative value, it would mean that the graph is approaching negative infinity. So we're not going to leave this limit as equal to 2 over 0. So we're going to rewrite this as the limit as x approaches 1 from the left of h of x is equal, and we can see from the graph that that's going to be equal to negative infinity, but just to confirm, using a test value. So a value directly to the left of 1 could be like 0.999. So if we were to, and I think this would be easier to do in the factored form of the equation for h of x, right? Because the numerator won't factor, but the denominator would factor to x minus 1, x plus 1. So thinking about substituting that 0.999 into our function, so that would be 0.999 squared plus 1 over 0.999 minus 1 times 0.999 plus 1. Well, the numerator would be positive, right? The numerator would be positive, and then the denominator would end up being negative because this factor here would be negative, and this factor would be positive, and a negative times a positive is negative. So that actually indicates that since we chose a value directly to the left of 1, that indicates that h of x is going to be approaching negative infinity. And we knew that it was either going to be approaching positive or negative infinity when we tried direct substitution in the first place, and we got a number not equal to 0 in the numerator and 0 in the denominator. Okay, so same thing happens for as x approaches 1 from the right. So we already know that we run into a constant, a non-zero constant over 0. We know there's a vertical asymptote. So if we wanted to choose a value directly to the right of 1, since this is the limit as x approaches 1 from the right, we could do that. So I'm going to pick like 1.001. Square that plus 1 over 1.001 minus 1 times 1.001 plus 1. Okay, and it looks like the numerator would be positive and the denominator would be positive as well. Therefore, the limit as x approaches 1 from the right of h of x would be equal to positive infinity. You don't need to put the plus sign in front of infinity. You can just put the infinity. It's implied that it's positive. So what is the limit as x approaches 1 for h of x? Well, our one-sided limits don't match. Our one-sided limits both don't exist, but we were able to state why they don't exist. But since those one-sided limits don't match, so it would be good to state the limit as x approaches 1 from the left of h of x is not equal to the limit as x approaches 1 from the right of h of x. Therefore, our two-sided limit is just DNE. That's all we can say about it. Now from pre-calc, we know that graphically at x equals to 1, there is a vertical asymptote. And that has to do with taking our equation for h of x, right, x squared plus 1, and then factoring the denominator. There's no common factor, right? There's no whole at x equals to 1. But we're able to see that 1 would make the denominator equal to 0 and therefore would correspond to a vertical asymptote. And then -1 would also correspond to a vertical asymptote because if we plug in -1, we would get 2 in the numerator again and 0 in the denominator. So there is a vertical asymptote at x equals to 1 and x equals to -1. The question just wasn't asking about that. So what seems to be the connection between the infinite limit and graphical manifestation that is mentioned above, the vertical asymptote? It seems that when there's an infinite limit, that means that there's going to be a vertical asymptote at whatever c is. Okay, remember our pre-calc definition of a vertical asymptote is let f and g be continuous on an open interval containing c. If f of c is not equal to 0 and g of c is equal to 0, there exists an open interval containing c such that g of x is not equal to 0 for all x in c in that interval, and the graph of the function h of x equals to f of x over g of x has a vertical asymptote at x equals to c. That sounds really complicated, but what it basically says is if you plug in c and f of c is a non-zero real number, then, but g of c is equal to 0. So if you get a constant that's not 0 over 0, then a vertical asymptote exists at x equals to c. Now we can add to our toolbox the calculus definition of a vertical asymptote, where if f of x approaches infinity or negative infinity as x approaches c from the left or the right, then x equals to c is a vertical asymptote on the graph of f. And notice this is important. So if, as x approaches c from the right or the left, so as long as one of the one-sided limits is approaching positive or negative infinity, it means that there is a vertical asymptote or, remember, an infinite discontinuity at x equals to c. So we can still identify vertical asymptotes in the same way that we did before, but now we have this new perspective that we can add in. So just to kind of review, these are basically like algebra pre-calc problems, right? Without graphing, identify the vertical asymptotes of each of these functions. Okay, well, g of x is a rational function. Just looking at that, I see there's no common factors. I could factor the denominator, but that's not even necessary. I could determine that there would be vertical asymptotes at -4 and 4 just by inspection, looking at the denominator and thinking about what values would make the denominator 0. So we have vertical asymptotes at x equals to plus or minus 4. So 2 different vertical asymptotes for that function. For j of x, Well, the numerator is a constant, so there's definitely no common factors. I want to see if the denominator factors. So x minus 7, x plus 1. Oops. So we would have a vertical asymptote at x equals to positive 7 and x equals to negative 1. For h of x, okay, factor the denominator. That's a difference of 2 squares. So there's a common factor that will cancel. That indicates, remember, that there would be a whole at x equals to negative 5. So this simplifies to be 1 over x minus 5. There's the whole at x equals to negative 5, but at positive 5, there would be a vertical asymptote. That would be 1 over x. So that graph will look like 1 over x shifted to the right 5 units. And then there would be a whole at x equals to negative 5. Or a removable, I shouldn't say whole, I should say removable discontinuity at x equals to negative 5. Okay, let's look at t of x. Let's see about factoring. So x minus 5x plus 3 in the numerator, and then the denominator would be 2xx. So that would be plus 3 minus 5 to get the minus 10 minus, or plus 3x, yep, would give us the negative 7x. Okay. Oh, there is a common factor that indicates removable discontinuity, whole at x equals to positive 5. So this simplifies to be x plus 3 over 2x plus 3. So there is a vertical asymptote at x equals to negative 3 halves, or x equals to negative 1.5. And then for tangent, okay, well you have a couple options here. Tangent is a function that you should be able to recall what its graph looks like. So remember, it's a periodic function, so it repeats the same pattern forever and ever and ever. But it passes through, tangent passes through the origin. So if this is pi over 2, half the period to the right of the origin, half the period to the left of the origin. Vertical asymptotes, negative pi over 2 and pi over 2. And then, right, that pattern repeats. So if you remember from last year how to identify the vertical asymptotes, we would say that there would be a vertical asymptote at x equals, pick one of the vertical asymptotes, so like pi over 2, and then add multiples of pi, the period of tangent. So pi times n, and define n to be an integer. The other approach that you could have used here is the fact that tangent is equal to sine over cosine. So you would basically solve for where cosine is equal to 0, which you could come up with that general solution set using inspection. So since 0 is a unit circle value, you know that at pi over 2 and 3 pi over 2. So you could say x equals to pi over 2 plus pi n, or you could come up with the two separate solutions, right? So it would end up being x equals to pi over 2 plus 2 pi n, or x equals to negative pi over 2 plus 2 pi n, where n is an integer. Both of those statements together could represent all the vertical asymptotes, but they could be combined into this. So that's better. And you should know what tangent looks like, right? Let me get rid of this Okay, determining infinite limits. Let's find each limit without graphing. Okay, so notice if we try direct substitution, this is the limit as x approaches 1 from the left. So if we try direct substitution, we get -2 over 0. That tells us vertical asymptote, right? I would, because we can factor the numerator here, I would do that. So I'm going to rewrite with the limit x times x minus 3 over x minus 1. That shows me no common factors. And then I would do some side work and do the test value directly to the left of 1. So you could use 0.999, you could use 0.99. There's a value directly to the left of 1, and we want to see whether it's positive or negative to determine whether we can say this limit is equal to positive or negative infinity. We know it's one or the other. So if I did 0.999 times 0.999 minus 3, 0.99 would work fine too. 0.999 minus 1, okay, so that's a positive times a negative will be a negative in the numerator. I'll put it over here. Negative in the numerator. And then the denominator would also be negative. So that indicates positive infinity. So this would be positive infinity. And then, same function, just the limit as x approaches 1 from the right this time. Okay, so using the same factored form of the limit, I'm going to do my side work. Oops. And directly to the left, or sorry, directly to the right of 1, sorry, this should be plus now, right? Directly to the right of 1, I'm going to use 1.001. So I would have 1.001 times 1.001 minus 3 over 1.001 minus 1. So the numerator would be negative and the denominator would be positive. Negative divided by a positive is a negative, therefore this limit would be equal to negative infinity. I should have done vertical steps for these, so I'm going to move this underneath and this underneath. So both of these limits are D&E. This indicates that there is a vertical asymptote at x equals to 1. Because these the one-sided limits are approaching different infinities for the two-sided limit. So as x approaches positive 1 of x squared minus 3x over x minus 1, all we would be able to say is D&E. Okay, properties of infinite limits. So let C and L be real numbers and let f and g be functions such that the limit as x approaches c of f of x is positive infinity and the limit as x approaches c of g of x is L. So one of the limits, limit of g, exists and the limit for f of x as x approaches c is infinity. So if you are adding or subtracting functions, like you have a function that you can think of as a sum or difference of functions, and one of those functions is approaching infinity, then that means the entire function is going to approach infinity or negative infinity. It works the same for negative infinity. For a product, so if you get one of the factors of the function is approaching positive infinity and the other is approaching a limit, that means that the product is going to be approaching positive infinity. So if the limit is positive, then it would be approaching positive infinity. If the limit is negative, the limit that exists is negative, then times infinity would be negative infinity. And then for a quotient, a function that you can think of as a quotient of two functions, right, a ratio of two functions, if the limit of the function in the denominator is approaching infinity, so it's increasing without bound while the limit in the numerator exists, then all we can say about that limit is that it is equal to 0. So similar properties hold for one-sided limits and for functions for which the limit of f of x as x approaches c is equal to negative infinity. Okay, so we have this limit where this function that we're taking the limit of can be thought of as a difference of two functions. Applying limit properties, we could also think of taking the limit as x approaches 0 of 1 and then minus the limit as x approaches 0 of 1 over x squared. Well, the limit as x approaches 0 of 1 would just be 1, but the limit as x approaches 0 from 1 over x squared, that was that first function we were looking at, well, that approaches positive infinity. Well, 1 minus infinity, because that minus we can say is equal to negative infinity. Okay, one-sided limit here. Remember, we always want to think about using direct substitution to see if we get a number. So in this case, we could also think of this as taking the limit of the numerator and then the limit of the denominator as x approaches 1 from the right. So if we use direct substitution in the numerator, we get 2. And then the limit as x approaches 1 from the right of cotangent. Well, if we plug in 1 for x, so if you use direct substitution, cotangent of pi is the location of a vertical asymptote. And thinking about the graph of cotangent as x approaches 1 from the right, that would end up being, so that would end up being positive infinity. Okay, and then 2 over positive infinity, well, that's going to be 0. Okay, and then our limit as x approaches so as x approaches 0 from the left, so I know that cotangent has a vertical asymptote at x equals to 0, just from my knowledge of cotangent. So as x approaches 0 from the left, cotangent would be decreasing without bound, so it would end up approaching negative infinity. And then as x approaches 0 from the right, for this function that is a sum of two functions, we could think about splitting this So the limit as x approaches 0 from the right of x squared plus the limit as x approaches 0 from the right of 1 over x. So using direct substitution for that first limit, and then 1 over x is a parent function you're very familiar with. So as x approaches 0 from the right, this would be going to infinity. And therefore, we can say that this limit is equal to infinity. And that's it.